Hello, and welcome back to another Evolution Simulator video. It's been a while. The biggest change in this new version of Evolution Simulator from the previous versions is that it runs more time efficiently. I did this by replacing the previous Evolution Simulator's object-oriented code with a matrix-based structure. In the previous version of the code, every time the simulation was performing a simple action, like a tree attacking another tree, it had to check the data types of the attack and defense values, even though we know beforehand that they're going to be numbers. That's not very efficient. This behavior is default because Evolution Simulator is written in Python, which has dynamic typing. When a programming language has dynamic typing, what that means is you can assign any sort of data type to a variable. Like you can say x equals a string, or x equals a number, or x equals a true-false value. But then every time you want to do some operation on that variable, you have to check what type the data in the variable is. However, because each bit of information about a tree is stored as a number, and because we know that trees exist in a grid-based structure, it's much more efficient to use a matrix-based data type where we can multiply whole lists and areas of numbers by each other rather than having to select them out individually and check their types. However, the one thing that I couldn't completely replace with arrays is tree reproduction, because each time a tree has a child, that's completely random. So because of that, the code is not necessarily as fast as it would be if everything were replaced by arrays. It's still up to 4 times faster though when the board is full, which is pretty good. As you can see from the scatter plot at the top right-hand corner of the screen, the trees are slowly evolving upwards into more attack or vampirism and less reproducibility. We know this because the cloud of points that represents the population genome moved from the bottom middle of the graph to the top left over time. What this tells us is that by survival of the fittest, trees that have evolved to attack each other rather than reproduce are more likely to survive and produce offspring, and thus they're more successful just by probability and random chance alone. Compared to the previous episodes of Evolution Simulator, I've updated the code to have more of a predator-prey type dynamic. That is, I've made it so that trees with attack can only attack trees with high reproducibility. Hence, trees with high attack can't really attack themselves, and so the marginal benefit of attacking each other when you're already in a population of predators is very low. I sort of like to think of this structure as bringing rise to a population of red lions and yellow rabbits, where the yellow rabbits breed more but are vulnerable to the lions. Over time, we'll notice that the black cloud of points in the scatter plot will gradually diverge into two separate populations. The top population being the lions and the bottom population being the rabbits. To be clear, this hasn't happened yet, but I'm cutting this video with pre-recorded footage, so 100% it will. If you want to see that, you can just skip forward. My best guess as to why the population is splitting into two groups is that lions don't like to hunt in packs. If you're a lion and you're next to many other lions, you're very unlikely to reproduce because you're not getting that benefit from being able to attack rabbits with reproducibility. The original goal of this series of Evolution Simulator videos was to try and engineer complex behavior from agents following a simple set of rules and to try and engineer some diversity just by survival of the fittest. Even though I haven't exactly recreated the structure of real-life predator-prey dynamics, it's very interesting to see that I can create something that behaves similarly just by only implementing a simple set of mathematical rules and interactions, and then just leaving it up to random chance. I think at this point we can sort of see that there are groups of yellow and red trees as well as the orange trees that have yet to evolve. Additionally, based on the scatter plot in the top right-hand corner of the screen, we can see that the two groups of trees are almost completely diverged, with only a few trees in between the genomes of the two groups. We notice that both the yellow rabbits appear to be clustered together, and the red lions appear not to be clustered together but rather formed into layers. This makes sense because rabbits have nothing to lose by being next to each other. But if a lion is next to another lion, then that's a space next to it that a rabbit won't be in, so the lion won't be able to have that benefit from being able to eat rabbits due to its high attack. It also looks like most of the red lions are surviving for a long time. If you just pick one group of red lions on the screen, you'll notice it doesn't appear to be changing a whole lot. This makes sense because if a lion is in a good position and it has lots of rabbits next to it can just feed on the rabbits and it won't die. If you guys would like to run this code for yourself, I have included the most recent version in a GitHub that will have a link in the description. Thank you for watching this Evolution Simulator video. If you have any ideas or thoughts, I'd love to hear them in the comments below.